Okay, so we got some kind of pressurized vessel. What that means is I have some kind of container. It's containing, doesn't really matter what it is, but it's causing stress on the metal or the material I have, and we can calculate what that is. The assumption in pressurized vessel problems is that we're talking about thin-walled tubes or thin-walled containers. And so we can use, these equations are derived based on thin-walled areas, approximations. Anyway, in this kind of problem, we're often given a strain in a particular direction, and we're given material properties and dimensions. In this particular one, it gave us Poisson's ratio, modulus of elasticity. We're given a ratio instead of an actual dimension, but we can still do that, and our strain. This little L here stands for longitudinal, which is this measurement here. And here's the derivation in case you're curious. We have our longitudinal direction here, and we have our radial direction here. And let you figure that out on your own time, but let's go ahead and solve this problem. Okay, so our three main equations here. This is a radial stress. This is our longitudinal stress. We saw the derivation for that. And all I did is substitute, instead of epsilon x, sigma x, and sigma y, I replaced it with longitude and radial directions. And that still works because they're 90 degrees from each other. They're perpendicular. So let's plug in our numbers. Equals PR over 2T minus nu PR over T divided by E. Now I can factor out the PR and T. Okay, let's plug in what we know. Okay, let's solve for P. Alright, let's put this in the calculator. And that gives me 10,000 pascals or 10 kilopascals, which is reasonable. And that concludes that problem.